Hi, I'm Zach. Today, I'm going to talk to you about a joint work with Bill Pfefferman in which we've proven that it's possible to eliminate intermediate measurements from a quantum algorithm in a space-efficient manner. Now, in order to explain our result, let's start by talking about the principle of deferred measurement. Suppose we have this very simple computation where we start with a single qubit in the zero state, and we apply this circuit to it, which consists of a Hadamard gate, followed by a measurement in the computational basis, followed by another Hadamard gate, followed by another measurement in the computational basis. Now it's easy to see that the result of the first measurement will be 0 with probably 1/2 and 1 with probably 1/2, and that the result of the second measurement, which we consider to be the output of the circuit, will also be 0 or 1 with equal probability. Now, the principle of deferred measurement tells us that it's sufficient to only ever perform a single quantum measurement at the very end of the computation. We can eliminate any intermediate measurements. Now, of course, this does not mean that we can just take the first measurement gate in our example here and rip it out of the circuit, because if we did that, then we'd end up with this circuit here, where now the result of the single remaining output measurement is always 0. And so these two circuits have very different output distributions. They are not equivalent. Instead, the principle of deferred measurement works by simulating each intermediate measurement using a fresh qubit and a CNOT gate. It's then easy to check that the output distribution of this new circuit is identical to the output distribution of our original circuit. These two circuits are equivalent. But how efficient is this conversion procedure? Well, if we only care about the amount of time that our algorithm uses, where by time we mean the number of gates in our circuit, then this conversion procedure is great, as replacing each measurement gate with a CNOT gate does not increase the number of gates. And so this procedure is time efficient. However, if we also care about the amount of space that our algorithm uses, that is, the number of qubits in which our circuit operates, then this procedure is terrible, as it costs us one fresh ancilla, that is, one additional unit of space for each intermediate measurement simulated in this manner. For example, suppose we have an algorithm that runs in log space and poly time, which is allowed to make intermediate measurements. By repeatedly applying this procedure to eliminate all of the intermediate measurements, we end up with a new algorithm which has exactly the same output distribution as our original algorithm, but which doesn't need to make any intermediate measurements. But how much time and space does our new algorithm require? Well, the original algorithm, which ran in poly time, might make polynomially many intermediate measurements. Each one of these measurements costs one additional unit of space to simulate, which causes our new algorithm to require poly space in addition to poly time. But this is an exponential blowup of the amount of needed space, which is extremely not good. And so the natural question, which has been considered by a whole collection of previous papers, is whether or not it's possible to eliminate intermediate measurements without a space blowup. Our first main result answers this question. Yes, it is indeed possible to eliminate intermediate measurements with neither a space blowup nor a time blowup. As our second main result, we exhibit new quantum log space algorithms and matching hardness results for a collection of natural linear algebraic problems. In particular, for a well-conditioned matrix A, we consider approximating the determinant of A, or the inverse of A, or A raised to some high power, and other such similar problems. By combining our quantum log space algorithms with our hardness results, we can show that all of these nice linear algebraic problems are complete for quantum log space. Moreover, this second result is actually the key tool we use in proving our first result about eliminating intermediate measurements. But before we delve into the details of these results, let me first spend a minute trying to convince you that space actually matters in quantum computation. Now, after several decades of progress, experimental quantum computers have advanced to the point where we're now in what John Preskill calls the noisy intermediate scale era of quantum computation, where intermediate scale refers to the fact that these quantum computers have few qubits. For example, consider a current state-of-the-art quantum computer, IBM's Q system, which has 53 qubits. In order to put that number in perspective, we can compare this state-of-the-art quantum computer with a not at all state-of-the-art classical computer, Apple's iPhone 7, which has 128 gigabytes of memory and has a retail cost of something like $400. Now, I don't know exactly how much IBM's Q system cost to build. There's some sort of trade secret, but I think we can safely assume it's a great deal more than $400. Of course, this is a somewhat unfair comparison, because when one says the iPhone 7 has 128 gigabytes of memory, that is conflating together multiple different kinds of memory. But the basic message is true. Current and near-term quantum computers have few qubits. They have a small amount of quantum memory. And so space really is important in quantum computation. Next, let's discuss why we actually care about eliminating intermediate measurements. First of all, quantum measurements are a natural resource, just like time and space are, and so it's desirable to minimize our use of this resource. Secondly, unitary computations are reversible, and reversible computation is desirable for a whole host of reasons. The ability to undo a computation by running in reverse is routinely used in both the design and analysis of quantum algorithms. For example, the tidy subroutine calling procedure or Wadrow's quantum rewinding technique. Moreover, reversible computation doesn't generate any heat, which is of practical relevance. Lastly, our result that it's possible to eliminate intermediate measurements without a space blowup shows the definition of quantum space is robust. The class of problems solvable by a quantum computer in a particular space-bound is the same whether or not intermediate measurements are allowed. In particular, consider the relationship between probabilistic space and quantum space. Now, it's easy to see that a general quantum algorithm, that is one which is allowed to make intermediate measurements, can just directly simulate a probabilistic algorithm, and so probabilistic space is certainly contained in general quantum space. On the other hand, before our result, it was unknown whether or not probabilistic space was contained in unitary quantum space, which was a rather peculiar state of affairs, as quantum computation should generalize probabilistic computation. Of course, as we can now show that unitary quantum space and general quantum space are equivalent, we immediately conclude that probabilistic space is contained in unitary quantum space, as we would expect. Next, let's try to make the definition of quantum space S of n a little more precise. Here, we're considering the class of languages recognizable by a uniform family of quantum circuits with two-sided bounded error in order S of n space. Now, for a space-bounded complexity class, either quantum or probabilistic, it's standard to limit the running time to be at most exponential in the space-bound, so as not to make the class unfairly powerful. And so here, we require that these circuits have only 2 to the order S of n gates. Now, we'll define 2 different complexity classes, which differ only in terms of the types of gates that are allowed to appear in these circuits. Firstly, we define BQU space S, which stands for bounded error quantum unitary space, which corresponds to the case in which only unitary gates are allowed. In particular, intermediate measurements are not allowed in this model. Secondly, we define BQ space S as our model of general quantum space, where now the gates are allowed to be arbitrary quantum channels. In particular, a general quantum algorithm can apply unitary gates and perform intermediate quantum measurements, where the results of those measurements can be used to control later stages of the computation. So we have these 2 potentially different complexity classes, BQU space S and the potentially stronger BQ space S, each of which is a reasonable definition of the class of problems that a quantum computer can solve in space S of n. We can show that these two classes, in fact, are identical. Any problem that can be solved by a general quantum algorithm in space S of n can be solved by a unitary quantum algorithm in the same space bound. In other words, we can eliminate intermediate measurements without a space blowup. Now, it'll be convenient to establish some additional notation for quantum log space. Namely, we define BQUL and BQL as the log space versions of these two complexity classes: bounded error quantum unitary log space and bounded error quantum general log space. We will directly show that BQUL equals BQL, which by standard padding argument then immediately gives us the general equivalence. BQU space S equals BQ space S for any larger space-bound S. For the remainder of the talk, we'll focus on quantum log space. Now we can start delving into the details of our result, beginning with the matrix inversion problem. Here, we're given an n by n matrix, A, and a pair of indices, I and j. The goal is to approximate the ij entry of A inverse to inverse polynomial precision. How hard is this problem? Well, the crucial parameter is the condition number, kappa of A, which is defined as the ratio of the largest singular value of A to its smallest singular value. Roughly speaking, if the condition number is very large, then even a small change in the matrix A can cause an extremely large change in A inverse, thereby making the approximation problem for A inverse harder. We want to focus on the easier case, when A is well conditioned, meaning that its condition number is not too large. In particular, suppose that A is polyconditioned. Then, as Harras-Steven-Lloyd showed for a somewhat different setting of parameters, namely sparse exponentially large matrices, this problem is in BQP. Then, building on the original poly-time Harras-Steven-Lloyd algorithm, Toshma showed that polyconditioned matrix inversion for n by n matrices is in BQL. This result was then improved by Deferred and Lin, who gave a BQUL algorithm for this problem, and also proved matching hardness results, thereby showing that polyconditioned matrix inversion is BQUL complete. We can now generalize this result even further and show that polyconditioned versions of other natural linear algebraic problems are also BQUL complete. To do this, let's consider the determinant problem. Following its original definition by Cook, the complexity class det consists of all problems reducible to computing the determinant of an n by n integer value matrix. Where, to be clear, we're now considering computing the determinant exactly. This class has many natural complete problems. Of course, by definition, determinant is complete for this class, but so is the problem of exactly computing the solution to the integer valued matrix inversion problem, matrix powering problem, and other natural linear algebraic problems. As we just mentioned, Deferred and Lin showed the approximation problem for polyconditioned matrix inversion is BQUL complete. We can then substantially generalize this and show that the polyconditioned versions of all of the standard det complete problems are BQUL complete. In particular, this will imply our results about eliminating intermediate measurements, as we'll discuss in a moment. Now, we note that simple reductions between the various standard det complete problems are well known. However, the standard reductions generally do not preserve the property of being well conditioned, and so they're not suitable for proving BQUL completeness. Instead, we will have to exhibit reductions which are somewhat more exotic. However, we first consider an easy case for which a simple reduction is possible, the well-conditioned matrix powering problem. Here, we're interested in approximating a single entry of the tth power of some matrix A, where t is polynomial in the size of the matrix. We also have a promise, which is that the various powers of A have polynomially bounded norm. This promise is the appropriate analog of the polyconditioned criteria for the powering problem. Now, there's a very simple reduction from this problem to the polyconditioned matrix inversion problem. As we already know that polycondition matrix inversion is in BQUL, we then immediately conclude that polycondition matrix powering is also in BQUL. The reduction makes use of the following matrix B. This is a block matrix where all the blocks are n by n. Along the main diagonal, we have copies of the identity matrix, and immediately above the main diagonal, copies of negative A. The rest of the matrix is all zeros. It's then easy to check that B inverse has a very nice form. Along the main diagonal, we have copies of the identity matrix. Immediately above that, copies of A, then A squared, and A cubed, and so on. Therefore, by sizing the original matrix B correctly, we can obtain a copy of A to the T in the top right corner of B inverse. Moreover, it can be shown that B is polyconditioned. And so we really do have a reduction to polyconditioned matrix inversion. This idea can then straightforwardly be extended to the well-conditioned iterated matrix product problem. This problem is like powering, except now we consider the product of polynomially many, potentially different matrices. Using a similar idea, we can reduce this problem to polyconditioned matrix inversion, and therefore conclude that this problem is also in BQUL. Additionally, we can show this problem is BQL hard. To see this, simply note that a general quantum circuit is just a sequence of arbitrary quantum channels. Each one of those quantum channels corresponds to a single matrix, and applying the entire circuit corresponds to the product of those matrices. Moreover, it can be shown that this problem meets our criteria of being polyconditioned, and so BQL hardness follows. By combining the two previous observations, we conclude that BQL equals BQUL, which, by standard padding argument, implies the general equivalence. BQ space S equals BQU space S for any larger spacebound S. In other words, we can eliminate intermediate measurements without a space blowup. We can also show results for RQL and NQL. These are the one-sided bounded and unbounded error versions of quantum log space, as well as for the QMA and one clean qubit versions of BQL, RQL, and NQL, though I'll refer you to the paper for details. I'll conclude by talking about the well-conditioned determinant problem. Here, we're given a polyconditioned matrix A, and we're interested in approximating the log of the determinant of A to inverse polynomial precision. We can show that this problem is BQL complete, and more generally, we can show that the polyconditioned versions of all of the standard deck complete problems are BQL complete. As mentioned earlier, the difficulty is that the standard reductions between the various deck complete problems generally do not preserve the property of being well conditioned. We exhibit a collection of new reductions which do preserve this property. Our reductions make use of a variety of different power series approximation techniques, and we also exploit a quantum algorithm's ability to operate on a very succinct representation of a big piece of data. Now, in order to put our result in the proper context, we note that Boyd, Sarah, Elder, and Maribon have recently shown that polyconditioned determinant is in deterministic space log squared n, poly log log n. Their results also made use of power series approximations. However, in this setting, quantum algorithms seem to have a significant efficiency advantage over deterministic algorithms, which enables us to put this problem in quantum log space as opposed to deterministic nearly log squared space. Moreover, we have a direct improvement in their result, as we've placed polyconditioned determinant in quantum log space, which is contained in deterministic log squared space. Lastly, we ask if it's possible to improve the dependence on the condition number for these results. If it is, that would imply a new best classical upper bound on quantum log space. Thank you for listening.